You'll have to break away while you're working on part of it and finish your cinnamon toast. So we were on the trapezoid, right? Here, and we have here and here, and we were understanding the trapezoid went like that. 3 to -3. We had coordinate points, and we had x, y. It was an isosceles trapezoid. So I think we had a different color to make it a little easier to see. And since it was isosceles, what we know is that this x here, you would go over some x and get out a y, over -x and get out a y. And we were understanding, we were trying to find the area, right? Was that the thing we wanted to show, that the area? And I think that's kind of where we ended, was we had 1/2 for our area, 1/2, and then we know the formula is base 1 plus base 2 times the height. Nate reminded us of partially of that. The height of the trapezoid would always be found by the equation of the curve, because to get from here up to here, you just go over some x up to that y height. And the y height was it 9 minus x squared? And then base 1 plus base 2, that's where we consolidate. It has was it 6 minus 2x, I believe? And, or plus 2x, right? 6 plus 2x. Because, and then we analyze that to understand where does the 6 come from. We said it was 3 minus a -3, so that gave us that base. That stays fixed. This base, depending on where you move the points, that base would change. So it would be just, if you moved it up here and over here, since it's symmetrical, this x and this x are the same, just the difference of signs. So the distance would be found by x minus a -x, and so that would give us the 2x. And that's where we get the 6 plus 2x is the two bases. So this is base 1 and base 2. All right, so that gave us our area formula. Then it says, show that the trapezoid has its greatest area when x equals 1. Greatest area, okay? When we talk about greatest, it's all another word for the word greatest that we've been working on. What's the mathematical word that we've been working on in 20-2? Max, yeah. So where it has its maximum. Well, if you think about this, okay, when you go, what kind of graph is this going to be? Line? I know you're on camera, so don't say anything. I'll help you. Parabola. No. Tempting for the uneducated, but you're educated.
For the uneducated.
Why is it tempting for the uneducated?
Because you see an x squared.
Yeah, you see an x squared and you're like, oh yeah, parabola. But what do we know is going to happen when you FOIL together?
It's going to be an x squared.
Yeah, you're going to get an x cubed. Okay, so that in some ways is important, isn't important. But what is important is to understand that you're going to have some sort of curve. And so in that, if we were to graph the area equation, remember, this is not the area equation. That's just your parabola with a isosceles trapezoid inscribed. It's saying, show that its maximum is when an x is equal to 1. Okay, so then its maximum area would look something like this. Actually, no, it's inscribed, isn't it? I'm sorry. So then it would look like that. That will have the maximum area. They tell you it's when x is equal to 1. So what that tells us is that if there's a maximum at x equals 1, if we were to graph the area graph, this function, it would tell us that at 1, what is happening? This is going to be a question for you. At 1, what's happening?
It's the max.
It'll be a max. So what will it look like? I mean, I know you can't, you could draw it with your finger in the air. What will it look like? The general look of it at x equals 1. So at x equals 1, let me ask you, are we going to have this or are we going to have this look? Which one? This one or this one? Top or bottom?
Bottom.
Bottom. Okay. So I've identified that. It's going to look like that. Now, will the graph look like this down here, specific in that spot? Or will it look something like this up here? At 1, right, so at 1, if it was saying at 1,
Oh.
a maximum here, a maximum here, is it going to be the top graph or the bottom graph? This is our area graph.
So it has to be positive area though, right?
It has to be positive area.
Yes.
Yes.
Let's go.
So if this is the area graph and you chose the bottom, which none of you did because nobody spoke, it's good.
Yeah.
If it's the bottom, that would represent over 1, down some amount, you would have a negative area here. They already told you the maximum occurs at 1, therefore it has to work. It has to have a positive area. Now, in this case, the rest of the graph, I mean, it's gonna, if it's cubic, it doesn't look like a parabola, does it? What does it do?
The, like,
Something like that, right?
Yeah.
Now, we could figure out where it goes through, absolutely. Why would this be easy to like figure out where it goes through on the x-axis? Let's actually graph it. Where does it go through on the x-axis? I heard a -3.
And then plus or minus 3, so then negative 3 is a double root. No? Okay.
Double root means it has to occur twice.
Mhm.
There's only 3 roots. What are the 3 x-intercepts? We were partially on the right track, and then we went off track. What are the guys? Find the x-intercepts for them. This is. I'm sorry. We're back to. This is shouldn't be a struggle here. This is like find the x-intercepts. Go ahead. I'm gonna make your cinnamon toast. There's between 6 and 5 of you in here. Find the x-intercepts. Confer with each other. We can even pause on the video so it doesn't sound bad.
It's plus or minus 3 and then negative 3 again.
Yeah.
Yeah. So
What was
negative
it?
3 is a double root.
Yeah, that's what I said. I'm so confused.
For the. So what are our 3 roots?
3.
Negative 3 and 3.
Yeah, so
Negative
negative 3 is a
3.
double root.
I thought you said.
Oh,
That would be mine. I thought you said 3 was a double root.
No. I was like, I'm sure I did that right, but okay.
Okay, so good. You confirmed with each other. Since Emerson's the only one speaking, she spoke, and then everybody agreed with her, but nobody would voice their.
Well, you said that I was
Yeah,
wrong.
you said she was wrong.
So everybody was like, oh shoot.
Well, apparently she wasn't wrong.
Yeah.
So, right, 3 is not a double root, -3. Okay, so go ahead, graph them. You know where the x-intercepts are. If without a graphing calculator, how would you find what the shape of the graph looks like?
You find if it's positive slopes or negative slopes and determine.
Okay, yeah, you could do the derivative, which you're going to need to anyways. So find the derivative of this. With this, when you go to find the derivative, do we have a derivative capabilities when you have multiplication between the variables? Like you see up there. Have you done a derivative of one like that?
To
No.
distribute for.
Yes, distribute first, then do the derivative. Very good. Distribute first, then do the derivative. This is going to be crunchy toast.
Sounds good.
Yes, that did not go as planned. Boil it out. Distribute that one. You'll need to distribute the 1/2 in as well. Make sure that's distributed in. then take the derivative. Confer with each other what the derivative is, and then when I say you're wrong, you can all disagree.
You can't disagree.
Wait, I'm confused where you're. Oh, because you changed the word now. Yeah, it's all the same except for this one. I can't write in text right now. I wrote this one was. You're like red. Thank you. Are you like outside like all lunch? No, your face is so red right now. No,
Okay.
Burn, dude. I was inside. That's so weird. Are you good? Yeah. I was just
You want
outside
toast?
for like
Me.
2 hours.
Yes.
yesterday.
Even though it's crunchy?
Yeah, I'll take it.
I cut off some of the intense crunch part.
Okay, thank you.
Actually, not the intense crunch part, just the blackened crust.
The black.
You
Ta-da.
did that extra work.
Preston,
Yeah.
Oh, no thanks.
who else wanted some?
Yes.
Lexi, did you want some?
Oh, it's not mine.
Thank you.
What'd you say?
Okay.
No, yeah.
Oh, okay, I was.
Preston said he's full, and I said full's not enough. I can't figure it.
Let's test that
Yeah,
theory.
Preston, you are never full.
We did.
Preston, think of the games.
Well, what?
Think of the games. Take yourself a piece of toast.
I know, but I didn't ask for one originally, so it wouldn't.
That's
that
the one
why?
right here.
Take it.
You sure?
Take it.
Yeah.
See, you're not full.
I'm not full.
Okay.
So they lied?
It's sinful to lie.
Cheese presents.
Alright, so we ended up determining, okay, very good. X equals -3 plus or minus 3. We apologize. -3 is the double root 3 there. So you know that the max is occurring over here. They already told you. But if you found the derivative, so let's do, what did you, after you foiled, what did you get for the foiling? Not the derivative, but what did you get for the foiling?
27 plus 9x minus 3x squared minus x cubed
27 plus 9x.
minus 3x squared minus x cubed.
Anybody agree or disagree?
Agree.
Agree. Okay.
Yep.
What's A prime?
Negative 3x squared minus 6x plus
Okay.
Obviously, I
Very
didn't
good.
get that way, just.
So what that is that's the derivative. If we set the derivative equal to 0, what are we finding when we set the derivative equal to 0? When you set the area function equal to 0, you're finding the x-intercepts.
Local maxes and local.
Yeah, you're finding local max and mins. What do you know one of the roots should be?
One.
Should be 1, if we did it correct. What can we divide everything by?
3.
I'm going to divide it right. I'm going to divide it by a -3.
Oh, smart. I didn't do that.
Smart.
Okay.
You know what, Emily? I don't want to hear.
And then what do we get when we foil? +3 minus 1, I mean not foil but factored.
Mm-hmm.
So we end up with x is equal to 1 and
Negative.
-3, which, as pointed out, we have a double root, so it doesn't make sense that at -3 you'd have some sort of max or min. Yeah. So based off of the fact we know this is a max over here, we could graph it, but you can also tell that if this is, you can either use this right here for our derivative or this. If you plugged in a -4, what do we end up with? Positive or negative slopes if you plug in a -4?
Positive.
Positive slopes.
Pretty sure.
Okay? So positive slopes, positive slopes. If you plug in, let's say, I'm sorry. Yes, there. If you plug in, I was looking at that's our x-intercept and our maximum. So then the other one's going to curl on here. If you plug in like 0, you end up with a negative, therefore your function goes like this. So now in this,
We were plugging -4 into the x squared plus 2x minus 3 equation.
yeah,
I just put that in my calculator and it's like, if you put in -4,
if you plug in a -4 there, that would give us 16 minus 8 minus 3. It should be
which is
positive. If you plug in like -2, it'd be negative slopes.
That doesn't look right.
Something's not looking right because we know the maximum needs to occur at or a positive one. I don't know why I wrote negative one.
well,
Well,
maybe I shouldn't have mentioned.
let's just double check our work here. Let's start with this.
Plug
Let's-
in your calculator.
Well, we could do that, but let's go -3 and 3. If we're using the derivatives to look at positive slope, negative slope, if we kept going with that, if you plug in 0, you'd get out a negative, so it should have a negative slope. If you plug in 1, you'd get out a, you get a slope of 0 at 1, right? Which would be there, and then it would come up like this, which would match our x cubed graph. And then if you plugged in, 2, you would end up with a positive, which would be positive slopes there. So that goes like that, but that maximum area, does it say maximum area or minimum area? Greatest area when x equals 1. So when x equals 1, the greatest area isn't matching. So let's do this. What's another way without derivative? Because we did the derivative, see if the slopes are positive or negative. What's the other way without the derivative to figure out, if we go -3 and 3?
Just a sine graph?
Yeah, a sine graph. If you plug in, now remember if you plug in a sine graph, you're wondering positive or negative. If we go with a -4, you're plugging back into your original. If you plug in -4, what do you end up with, a positive or a negative? You end up with a,
You plug in what?
what would you plug in? I should ask you what, -4, sure. You can plug in -10, anything to the left of -3, you're looking for positive or negative. Not slopes, but the sine graph now, not a slope graph, sine graph. So if you plug in -4, what do we get back out? A positive or a negative?
Positive.
It's definitely a positive. Wait.
It's a positive.
Yeah, it's positive, right?
Yes, I did.
Okay?
My brain.
Yeah, same.
And
Oh yeah, yeah, because if you plug in a -4 here, you'll get out a negative here, 9 minus 16, -8, and 6 is -2, so you get a negative and a negative. So you'll end up with a positive. What do we expect here then?
Negative.
Definitely a positive because this is a
Oh, yeah.
double root, but let's check it. If you plug in 0, what do you end up with?
Oh, yeah.
Positive. And then what do we fully expect then? So we're actually expecting this, and then up to max out at 1, and then down through like this. That's what we're expecting. Now, the issue is that somewhere along the way, something went wrong in our derivative.
Right.
So in that, let's just double check. Because if the derivative says it should be positive, these are all negative derivatives. So let's double check our work. A is equal to 1/2 9 minus x squared, 6 plus 2x. Okay, so A is equal to 9 minus x squared, 3 plus x, right? The 1/2 goes in there. So A is equal to 27 plus 9x minus 3x squared minus x cubed. So A is equal to negative x cubed minus 3x squared plus 9x plus 27, which is plus 9x minus 3x squared minus x cubed. So then we go A prime is equal to negative 3x squared minus 6x plus 9. Okay, and then if we set it equal to 0, negative 3x squared minus 6x plus 9, that matches still. And then what did I do? I divided everything by negative 3, which would end up giving us x squared plus 2x minus 9, minus 3. Which, again, these max and mins match what we want. So we did that correct. So everything's matching. So 0 is equal to x squared plus 2x minus 3. X would be equal to, okay. So that now matches. So our derivative, if we plug into the positive is not representing the derivative because that was our sine graph we were just discussing. Okay, so the derivative though, if we plug in, let's try it again, plug in something negative 4. We said a negative 4, 16 minus 8 minus should be positive. What if we plug in a negative 4 to here? There we go, bingo. What if you plug in a negative 4 to here? As opposed to here. What do we get back out? For A prime plugging into here, a negative 4 into this one.
Negative.
You get out a negative. And then if you plug in, so we would get out a negative for the derivative part. And what happens when you plug in 0? We should get out a positive. Sure enough, you get out a positive for the derivative part. Then if you plug in 2, sure enough, you will get out a negative and then a negative for the derivative part. So something I probably should know, but I'm thinking, and maybe I've run across this, but maybe just make a note for us. When you're plugging in the derivative, go back to the original function before you divided out a constant. We didn't divide a variable out. I'd have to think through why that is the case. Oh, that's why. Because when you set it equal to 0, you're just finding where it's maxing out and miniming out, and it doesn't. 0 is neither positive nor negative. But here, when we divided the derivative by 0, what if we took the original function here and divided everything by a negative 3, the negative also should have gone over to the other side.
But it wouldn't make the 0 negative.
But it wouldn't make the 0 positive or negative, so it's actually changing the sign of the derivative when you do it this way, where we're not really worried how steep, like dividing by the 3 technically is there as well, divided by a negative 3. But we're not really worried how steep it is, which that 3 would play into, but we're worried about where it's positive or negative, so that negative should have actually been over there. So that's a good note for us to make, myself included. Don't go back to the original derivative, not after you've manipulated dividing by a constant. But it won't change where your zeros happen in terms of maxes and mins. So when it says though, show that its max is at 1. This is what they want you to show, is the process of here to a derivative, and then the derivative to here, which is fine. It's fine that we manipulated it to find where it's maximizing and minimizing. And you would say like this, and then to show that it's a maximum, you would find, obviously, you could actually just state at x equals, well, you could go at x equals -3, you get out y equals what, and then at x equals 1, y equals what, and therefore this one is going to be a higher value than this one, because we already know at -3 we get out 0, and y equals, what do we get out for y when you plug in 1? What do you get out for y when you plug in 1? You have two equations to plug into. You could either plug into the derivative or you could plug into the area one. Which one would we plug into?
The area one?
Absolutely the area one. Because what are we looking for? We're looking for the local max. You're looking for the max. So what happens when you plug in 1? What do you get back out? What do we get back out when you plug in 1? What is it?
I think 32.
32?
I don't know if I did that right.
Okay? So therefore, when you look at this, you know that this would be your local max. You also know that it's a local max when you look at the derivatives. Now in a formal, like the calculus class or AP class, you would have to state, how do I know it's a maximum here versus a minimum? Well, you know it's a maximum because to the left of x equals 1, a prime is positive or negative. To the left of x equals 1, what is a prime? A prime is positive. So a prime is, we would say, greater than 0. The right of x equals 1, what is a prime? A prime is less than 0, it's negative. And where a graph goes from increasing to decreasing, so this was increasing, this was decreasing, where it goes from increasing to decreasing, what do you get back out? Or what do you get? You get a max. If it goes from decreasing to increasing, you get out a minimum. So in a formal class, you would have to understand that. So you couldn't, I mean, even if you used your graphing calculator and graph this, you would have to state the derivative is positive, therefore it's increasing, and then the derivative is negative, therefore it's decreasing. Between an increasing and decreasing, we know we have a local max. That's a rule that we've learned. So therefore, you know, local max of 32 at x equals 1, something like that. That would be the formal way to write it there, using the concept of derivatives. Okay, so that was great. We learned something new there. This would be the show that it occurs at x equals 1, and then this would be the formal explanation of why it works at x equals 1. Okay, now let's take a look at number 5. So these are some of your homework problems. Number 5, it says congruent squares are cut from the corners of a rectangular sheet of metal that is 8 wide and 15 long. And then it makes an open box. Okay. So a little picture proves helpful. There's a picture in the book there, but that picture lines up with what number? 6, yeah. So, but it's kind of the same concept, except I think on number 6 it's a closed top box. So on number 5 here, it says you've got a rectangular sheet like this. What are the dimensions? 8 by 15. And then it says you're going to cut out the corners, right? Of equal width, or equal dimensions, I guess. And make an open box, right? Fold them up and make a box. There's no way this has any memory left. It does. Wow. Okay.
It does.
Well, I was using the wrong camera. Okay. So what do we get here then? Do they tell you how much to cut out?
No.
Do they tell you a variable to use? X. So you're going to cut out X here. How much would you cut out here? X. Alright? Otherwise it wouldn't make sense. You could, but you'd have a weird shaped box. Which there could be value in it for something, but not for what we're doing. Alright. Then, so we know X, X. Okay. Then what did it state?
Express the volume of box function of X.
Okay, so they don't give you the volume.
Mm-hmm.
So what they're not stating is show that it matches, like we did with the area formula. We just showed, oh yeah, H was this, and you know the base one was this. They want the volume, express the volume as a function of X. So what is that in function notation? What does that look like? What variable will I use? Variable